Okay, here we go. All right. So now we're going to continue on to session number 8, normal loading 2. All right. And today we're going to introduce using finite element analysis, okay, for problems of normal loading, and then we'll get into thermal strain and stress along a bar. Okay, so let's just talk about finite element analysis a little bit. Has anyone ever used finite element analysis? A little bit. Okay. All right. Anyone ever heard of finite element analysis? Well, okay. So, well, Aaron, you said a little. So, what, like in your mind, what is finite element analysis?
Simulating forces and solid.
Okay, simulating. Yeah. Okay, simulating forces, simulating loads on solid objects. All right. The reason we call it finite element. Okay. I mean, well, let's think of what would not be finite element. Well, you can think of continuum. Okay. We can think of our blocks, right? Our bars, our shafts, our rods, our beams, right? As being made of an infinite number of elements, right? Because we talk about these little blocks that are infinitesimally small. Well, finite element is saying we're going to break it up into a number of discrete elements that we can then approximate, right? Or use to approximate the behavior of the overall object. Okay, so you have to, choose a sufficient number of blocks in order to make this work. All right, and there are different commercial packages out there. There are many. Okay, we won't necessarily name them all or name them right now. Okay, but there are also nowadays there are some free packages out there that allow you to kind of get some familiarity and frankly they would allow you to do pretty good design work if you choose to use them. Okay, so what we're going to do today is we're going to use an engine, all right, so calculus, that is embedded in a couple of graphic user interfaces. Okay, FreeCAD has calculus in it as well, but we're just going to use FreeCAD for the creating geometry, and we're going to use PreProMax, okay, as a user interface to be able to look at the stress and strain in a bar that's being loaded with a force. Okay. So just a note, this is on a PC, all right? FreeCAD should work on both PC and Mac, okay? If there is another program that you want to use that does CAD, you're welcome to do that. What you'll find as we export to an STL file, all right, is that there are often some issues with the scaling. Okay, so we have to keep that in mind. PreProMax only works on a PC, unfortunately. But I'll show you how to run it. And if you go to the computer lab and you run Windows on one of those machines, you're good to go. All right, you can download it and you can run it almost instantaneously. Okay, and to be honest, I'm a little nervous about doing this because I ran out of time. I've done it before. You can see, like from previous semester, I've done it. Pretty familiar, but I know that our MS student Shivam, he has a nice tutorial. Shivam and previous TA Trevor, they have a nice video which you can see on the webpage and on the well, it's not on our YouTube channel, but we have a link in a playlist to their video. Okay. So okay, so let's go ahead and let's come up with a geometry, okay, based on these dimensions, all right, and we're going to apply this force, and we're going to use these material properties. And I am nervous because it's been a while since I've done this, so this could be embarrassing. But hey, it is what it is. So what do we do? So I've already installed FreeCAD. I haven't even run it for the first time on this computer or on this install. Okay, but I've installed FreeCAD, and so what you can do is you can, after you've installed it, you can go ahead and run it. And again, we're not using the FreeCAD for the finite element analysis, although you can. We're using it just to create the geometry that we want. Okay. So, and as they say, when you haven't rehearsed, be prepared to fail, essentially. So we're going to see how this goes. Okay, so here is the user interface for FreeCAD as you'll see it. And we're going to do a create new. All right. And in this case, you have options for multiple interfaces that you can use in FreeCAD. We are not going to do FEM. We're not going to do part design. We're actually going to do part. Part design is a little bit more like what you would see in your conventional 3D modeling. Okay, we're using extrusions, using cuts, those things. Yes?
Just curious, like you don't have to use FreeCAD, right?
You don't have to, but I'm going to show you that it's pretty simple if you do. Okay? All right? I'm going to try to show you that. Okay? So we open up part, okay? And I guess I challenge you in your other 3D modeling software to make a cube as fast, or a rectangular prism as fast. So we come over here, okay, and we're going to insert this object just like this. It's a cube, all right? And the dimensions that we're interested in are 5 centimeters, 1 centimeter, 1 centimeter, okay? So 5 centimeters, 1, 1. All right, so 5, 1, 1. All right, and you can even switch it to like Tinkercad if you like, or whatever your so there it is. Okay, that's the object. All right, pretty simple. And so what we need to do now is save at or export. Sorry, we're going to export this, and I'm just going to put it on the desktop. I know that's like not cool, right? And it's so not cool because my desktop is actually pretty clean right now. Okay, so now it's been exported as an STL. What we do next, or what you will do at some point, is you will go to PreProMax, just Google it, okay? You go to the website. So if you want to, if anyone wants to follow along, they're welcome to do so. Go to downloads, and I'm not a developer, so I'm not going to even touch that. Okay, and I'm going to download the PreProMax, and I'm going to save this. And what am I going to do? I'm just going to save it on the desktop. Again, really probably grades people the wrong way. Okay. So now I've got this file here, and I'm going to minimize this. And look, see, my desktop is actually pretty awesomely clean, right? I'm going to open this up, and we have to extract. Actually, I should have done it this way. We have to make sure you don't run it from the zip file. Make sure you extract it. Okay, this actually was a hang up for people in the past. So we're just going to extract this thing, and you don't even have to install it. You don't have to do like add or remove program or anything. It's just there, and it's an executable that you can run. Okay, so now we go into this folder that it's created up here, and we just double click on whoops, not like that. There we go. Okay, that took me. It's okay. I think it's okay. I hope you do too. So now we're opening up PreProMax. And this is, I mean, for open source free software, it's really quite nice. Really quite nice. And we're recording this, so don't worry if, you can go back and watch it tonight if you like. Okay, so what are we going to do? We have PreProMax here. We're going to create a new part, and I'm going to convert it over to meters, kilograms, seconds, degrees Celsius. Okay, we're not doing anything of that nature. I'm going to hit OK. Okay, still nothing in here, so now we're going to import. All right, and what are we going to import? We're going to import from the desktop. Oh no. Wait, what is this? Oh, it's an MF file. Whoops, I must have exported to the wrong type. Let's go back to here. We're going to export. Oh, sorry. Yeah, MF is not what we want. We want STL. So this one, we want STL like that. So again, really bad naming convention. It's an unnamed cube, which is not even a cube anymore. Okay. Unnamed cube. Yeah, good, it's there. So now we'll try that again. We come over here, we're gonna import, not from documents, but from the desktop. Boom, okay? Now, what did we just say that the dimensions were supposed to be? 5, well, go ahead, yes.
5, 1, 1.
Yeah, 5 centimeters by 1 centimeter by 1 centimeter, right? What did this come out to be?
50.
50 meters, all right? Okay, so that's not what we want, right? So if we want 5 centimeters, right, and we've got 50 meters, right, we're off by a factor of, no, 1,000, right? We're off by a factor of 1,000, okay? So what we're gonna do is we're gonna come over to this geometry, and we're going to come over and we're going to do a transform. So this is where if you do it in a different software package, you need to be careful about, well, even if you do it in this software package, if you do it in FreeCAD, you need to be careful about the scaling, all right? So we're going to scale, and we're going to scale by 1,000 in all 3 directions. What's that?
Oh, it's not. I'm just thinking out loud.
You're thinking you're not happy, right? So, so we're now zoom to fit, right? And now what do we see? Okay, it's about 0.05 meters in length, which is our 5 centimeters. Okay. Now, it looks really nice, but we got to do some work. Okay, so what are we going to do? Well, we're going to move over, okay, and begin. We can do a mesh. That's fine. So we're going to create a mesh like this, okay, and we hit OK. We're going to do it on the part. Or hit OK. Oh, sorry, I had to click it. There we go. Okay. Now, there it's not the greatest, okay, but it is a mesh, okay, and so you could do create mesh instead. Oh, I did yeah. Actually, I'm going to delete that. I think it's the same, but I'm just going to create the mesh instead, and this is why it's been a little while for me. Okay, like that. There we go. Okay, that's I can make it a little bit better. Let's go back. I hope I can go back. Okay. undo create mesh, and I'm going to do the meshing parameters. Okay, and here, okay, what we're going to do is we're going to I'm going to reduce the maximum element size down to 1 millimeter. Okay, and now we're going to do the mesh like this. Okay. Okay, so maybe that's a little bit extreme. All right, it's going to take a little longer to solve, but that's a pretty good looking mesh. Okay, if you can see that. Okay, so now, what's that?
That's just, they're all like elements.
Right. So now those are elements. It's been broken down into 34,638 elements. Do we really need that many elements for this? Probably not. Okay. So now, the next thing I can do is I'll come over here to materials, okay, and I'm going to use an elastic one right here. Bring that over, and now we have a Young's modulus. We're doing it if we go back here. Okay, we said we're going to use 200 gigapascals. What does this mean? It means that we're probably using steel. Okay, 200 gigapascals with a Poisson ratio of 0.3. So I think this thing is smart enough to do gigapascals. Yep, see that? And Poisson ratio is 0.3 and that's dimensionless. We'll hit OK. All right, so now we have our material in there. Okay. Now this is we want this is the original geometry. What we want to do is we want to say I'm going to make one side a wall, all right, and then I'm going to put a force on the other side, and I'm going to pull it. That's going to be our axial loading. Okay. So for that, let's go ahead and we're going to add a constraint. Okay, and we're going to go ahead and create a constraint. And it's going to be a rigid body, and we're going to, nope, that's not what we want. We want it on, and this is where so this is where I am now forgetting. No. Okay, create a surface. Okay. Here we go. Okay, so we created a surface there. Of course. Well, this is embarrassing. Okay, so no, that is not what we want either. Okay, let me see if I can. Nope. Okay, we're going to do static step for the load. Ah, here we go. That's why. All right, so here for the load, we're going to create a uniform pressure load. Okay. On the right. Oops, yes. On the right. Okay, and the pressure that we're going to use, okay, is going to be this 1,000 newtons divided by 0.01 times 0.01. All right, that's 1,000 newtons divided by 10 to the minus 4, so that's 10 to the 3, right? Divided by 10 to the minus 4, that gives us 10 to the 7. Okay, so what we're going to use is 10 megapascals. So I'm going to come over here. Okay. And we're going to say, okay, right? And it's going inward, right? So that's not the direction we want it to go. We want it to be coming outward. So we go over here. We're going to edit. And I'm going to change that to a minus sign. Okay. Now it's coming out. Over here, we have now what was missing before, because we now initialized the step. We're going to create a boundary condition. And this is going to be a fixed surface. And I'm going to select that surface right there. I hit OK. All right, so now it's good. Some embarrassment, at least temporarily, avoided. Okay, so now what we can do is we can create an analysis. And well, I guess we already have one. So we can go ahead and we can run this analysis. We don't need to create another one. We'll run it. Oh, we had to. Oh, okay. So this is, you don't want to do this. So we have to. We're going to close that. Right. No. Yeah, oh, that's fine. That's fine. They don't need a section. They don't need a section assignment. Okay. Oh, it failed though. That's not good.
It said there was no material.
The material I thought I defined appropriately. There. You could be. Why didn't it associate it with the I don't know if we want to do that. That I'm not familiar with. Okay, starting over. Importing. Geometry needs to be transformed. That's applied. That's that. Mesh is being applied. Go ahead and create mesh. Now we've got our part. Now we create a static step. We add our material. We add our boundary conditions. We add our load. We said that was -10. Okay, that's that. What?
Do you have to have it selected when you make the material?
That's possible. I'm not 100% sure. We can try that. It kind of went away. There's a part that I'm well, let me just go. I apologize, everybody. This is the beauty of a live demonstration. Sometimes I make mistakes. So if you go to, let's see, let's watch Shivam.
And click open up PreProm. There is usually some problem in unit conversions and
Yep.
all that. So we will scale our part up to match our dimension. To do that, geometry, then we will go in part, then transform, then scale. And we will be scaling in X, Y, and Z direction with 1/1000. We'll hit apply and we'll close. We'll go in zoom view and we'll hit zoom fit, and now you can see our part has accurate dimensions and it's ready for the analysis. So now we will create a mesh. We'll click on mesh, meshing parameter, and we can see it, and we'll hit OK now, and then we'll go create a mesh. So it will create a mesh pretty soon. So we have our mesh ready for the analysis, and it also opened up a few other things for us. So for our analysis, first thing we'll do is double click on materials. We'll select elastic and we'll give a Young's module of 10 gigapascals, we'll just add G and it will automatically add all the zeros and put Poisson's ratio of 0.3. Now we can also name this material. We'll name it steel, and we'll hit OK. Now we will select the section we'll use for analysis. We'll click on the section, then click on the. We are doing
okay.
So we'll click on
Okay,
the
that's what I didn't do.
We'll click on steps,
Okay,
and we have different.
that's what we did. Okay, let's go back. Okay, so we had to create a section, and we call it, it's just going to be on the whole part. Yes. There we go. Okay, now we've got this whole section, and we can run the analysis. All right, sorry y'all. Has a lot of elements, so it's taking it a little while. Okay, 30 seconds. Let's look at the results. Okay, and here you are. Okay, so what are we looking at here? Okay, and this is what you're going to do on the assignment, okay, tonight or tomorrow morning, is you're going to have a bar, okay, that comes in, and you're going to take some screenshots of different things. Okay? And so let's talk about the types of screenshots that you can take. So X is the one direction, Y is the two direction, Z is the three direction. Okay? And so right now it's giving us displacements in all directions. But if I just want the X direction displacement, then I can select U1, all right, and that'll give me the displacement in the X direction. If I want to know what the displacement is at a particular location, I can do a query. So that's right click, and I can select a vertex, for example. So I'm going to select a node like right here. Okay. So what is this saying? This is saying, whoops, okay, that at this node, all right, which is located at 5 centimeters down the line, all right, that was the initial mesh, it's saying that the value, right, for the X displacement, the value for the X displacement is 2.5 microns. Okay. Now, let's take a look at some other quantities we might be interested in. Strain, for example. Okay, so strain is going to be under this category, and this is, remember how we talked about the subscripts, right? If I want strain in the X direction, that's like an epsilon 1,1. Okay, so that would be what you have here. All right, so epsilon 1,1 tells me that the strain is 50 microstrain, 5 times 10 to the minus 5 at that end. All right. If we want the stress in the X direction, okay, we can do that as well. And that tells us that the stress in the X direction is going to be 10 megapascals, 1 times 10 to the 7th. All right, and that makes sense. That's what I specified. Right, so that better be that. Now, what's happening over here? Why is there such a variety? Why is there such a big range of the stress? Okay, that's because of what we call edge effects. All right, there are edge effects here. Remember, this is constrained on this side in all 3 directions. So you have Poisson ratio, right, telling that it's got to shrink a little bit in those directions, right? So it's going to be like, oh, I really want to shrink, but I'm not allowed to shrink. So the stress gets to be very high at this face where there are end effect. Okay. Now, what if we want to know how much strain or how much change in diameter there might be in an orthogonal direction? Okay. Let's say that we want to know the strain in the y direction. Okay. Then I do epsilon 2, and that tells me that that's the strain in the y direction, right? So that's how much strain there is in this vertical direction. If I want to know in the z direction, right, then I do an epsilon 3, okay? And if I want it on the top, right, I could do another query, and I can put another element wherever I want. Any questions on this? I apologize for the issues with the getting it to run. Okay. So we've taken a simple bar and we've added a pressure on the end, and we've been able to extend it. Okay. And so on the homeworks, you'll have an opportunity to kind of do these calculations. And if you look at Shivan's video, you also have insights, all right, into how to relate, right? And we can relate those, actually right here, you can see that we calculate these things out manually. So like epsilon y, right? A minus 15 microstrain. Is that what we see? Yes, that's what we see here, right? That's for, or this is epsilon z. If I want it for epsilon y, whoops. Right, if I want it for epsilon y, I do epsilon 2. Also, it's the same. If it's in the z direction or the y direction, it's the same. Okay, it's going to be minus 15 microstrain. It means it's constricting that much. Any questions? All right. Now, in the last 10 minutes, let me attempt to go through very quickly thermal expansion. Okay, and if I don't do a sufficiently good job, which is probably true here, please feel free to look at the prior videos, okay, which are available. All right. So, what is expansion due to a thermal load? It is a strain, right? So if I have an object in space and I apply some heat to it, it doesn't develop any stress. It's all strain. It just expands if it has no constraints on it. That may be a little bit counterintuitive. And that can be given by a term we call alpha, okay, times the temperature. This is a linear alpha L. That's a linear coefficient of thermal expansion times length gives us what the linear strain is. Okay? So that sounds pretty self-explanatory, right? Take an object, take a bar, heat it up, use the coefficient of linear thermal expansion, right, to be able to figure out what its new strain is. There are relationships between what we would consider linear coefficients of strain or coefficients of thermal expansion and volumetric, right? And we just did an analysis looking at the relationships between volumetric strain and linear strain, okay? We had the bulk modulus, right, that we were looking at. We had the dilatation that we were looking at. And so it may be a little bit counterintuitive, but if you go back to what we've derived previously, you see that the volumetric strain, the volumetric coefficient of thermal expansion is actually 3 times. It's not like using alpha L cubed, it's just 3 times alpha L. Now, if we have a bar that we heat, okay, we can go ahead and use this constitutive equation for the alpha L to figure out how much strain there is, and then multiply that alpha, or multiply that epsilon, right, that linear strain, times the original length, and that will give us the change in length. Pretty straightforward at this point. Is there any stress in this bar? No, there's no stress in this bar. This is a bar in free space. Has it changed its length? Yes, it has. Now, what happens if that bar is constrained? Well, it wants to expand, but it cannot. All right, so here we have a bar between two walls. If it were unconstrained, and so this is going back to kind of the method of superposition. If it were unconstrained, okay, then we know it would just increase its length, and there'd be no stress, no force, no internal stress in that bar. But there's a wall there that's pushing it, that's keeping it, it's pushing it closed, or not closed, it's pushing it so that it can't expand. And with that, there's a stress, okay? So you can think, now I've got this bar, and there are forces, and they're the same in this case, on either side of the bar to keep it from expanding. Those forces are what cause the internal stress. Well, we can think of that force causing that stress as the thermal stress now that we have induced because it's from a thermal load. And it's going to be in compression, right? Because those walls are wanting to compress it.
Is there no thermal stress if it's not constrained?
That's right. There's no thermal stress if it's not constrained.
But is there still a strain since it's changing in length?
Yes. Yes. Okay. So first we think in terms of thermal strain, and then we typically think in terms of thermal stress.
Does that mean that the whole E equals sigma over epsilon? Does that still work, or is
So-
like one of them would be zero? I don't know.
Well, yeah. So sigma is equal to E epsilon, right? So the stiffer the stress is going to be dependent on the elastic modulus. The higher the elastic modulus, right? If I'm constraining it, right, and I have to push harder against that elasticity of the material, then it's going to have a higher internal stress. Okay. Now, this is a complicated problem that is on the homework. All right. And let me just, in 3 minutes, which we have, talk about 2 ways to do this, okay? And then you'll have the opportunity to look through this. One way is through the method of superposition. Okay? The other is using geometric compatibility. Both of these techniques are described in these slides. Briefly, this first technique, using method of superposition, says I have 2 different materials and 2 different lengths with the same cross-sectional area connected to each other. And if I'm going to use the method of superposition, I'm going to first think about the unconstrained case where it can just expand. And so there's going to be just strain, no internal stress, no internal force in the unconstrained condition. And if I'm thinking about how much this piece moves to the right and how much this piece moves to the right, it's just based on the alpha delta t of that particular length, right? Now, if we think about delta 1, all right, as being the expansion of this piece, and delta 2 as being the expansion of this piece, and I think of the overall delta as being delta 1 plus delta 2, I can describe this delta here, and then by method of superposition, think I have to apply a force such that that delta, that overall total delta, is 0. Okay. These are bars and springs, bars as springs as well, which means that in this particular case, the force on this end and the force on this end, all right, there's no internal force being applied there. That force is going to be the same on both, and the force is the same throughout the members. Although the strain can definitely be different, and the deformation can definitely be different for those individual pieces. Okay, and so that's what this approach does. Okay, and you can go through this. And this is more on using that approach. Okay. The other approach, okay, is to use geometric compatibility. All right. So what we're saying is that we have some displacement here and some displacement here. We set those equal together, or we add them together, and the overall displacement is again 0.
Here's what I found.
Okay. So nothing has changed here in terms of, okay, we know that the displacement is going to be the same. But using this approach, all right, might be simpler, okay, in some respects, if we're interested in figuring out what the strain in these individual members is, okay, which can be given here. And it could also be simpler if I'm interested in figuring out what the displacement, say, of this middle is. Because if I want the displacement of this middle piece, then if I know the strain of this section, right, I can just multiply by the length, right? I can multiply by L1 to figure out how much it goes to the right. Okay, but we have to satisfy geometric compatibility. We have to use constitutive equations, and we have to definitely satisfy equilibrium. Okay, so that's pretty much it. This is the assignment problem. Okay, and I know it's a lot, all right, for one evening. Okay, but I'm confident that you'll be able to do it. I'll be on the group meet if you like to get in touch with me. All right, and I do believe that now you have all the tools that you need to be able to solve these problems. All right. If there's questions about PreProMax, again, I'm sorry that the demonstration did not go as smoothly as I would have liked. Okay, but you can look at Shivam's video that's up there, and then look at today's video as well. All right. Thank you.